This is video 16 in our series on tensor calculus. As a follow-up to the previous video, we're going to present a number of specific examples of the covariant metric tensor. We'll start with Cartesian coordinates. So let's set the stage just a little bit. First, we'll let our variables be x, y, and z, and our covariant basis vectors are just x hat, y hat, z hat. And we'll update our picture a little bit so those basis vectors will show up just like that. Okay, so now that we have our basis vectors, we will now derive the covariant metric tensor. So remember our equation, it's Zij, this is our definition, is going to be equal to z, the vector Zi, dotted with the vector Zj. So we're going to have every combination of dot product with each of these guys over here. There'll be 9 total terms when we're through. Well, like any other second-rank tensor, it's often easier to see it if we represent it as a square matrix. So let's do that. We'll say that Zi is going to be a square matrix. In this case, it's 3 by 3 because we're dealing in 3 dimensions. We'll call the rows I, the rows, and J, the columns. Okay, so how does it work? Well, the first thing we do is we have to find the dot product of Z1 dot Z1, and that's just x hat dot x hat. And that is simply 1. It's a unit vector dotted into itself. Okay, next thing, Z1 dotted to Z2 is x hat dotted to y hat. They're orthogonal, so that result is just 0. So row 1, 2 is going to be 0. Now, because the tensor is symmetric, we can swap I and j. We know immediately that because 1, 2 is 0, then 2, 1 is 0. We can go ahead and fill this in because the dot product of x with y is the same as y with x. So we only need to do one of them. Okay, now we'll take Z1, Z3, x hat dotted to z hat, which is 0, and again, if 1, 3 is 0, then 3, 1 is 0. So now we'll take the dot product of y hat with itself, that's Z2 dot Z2, y hat dotted with itself is just 1. Y hat dotted with z hat is 0, that's this guy, and its counterparts over here. And finally, z hat dotted with z hat is just 1. And so what you see here is the covariant metric tensor in Cartesian coordinates. Now, one of the outcomes here I want to show you is that these diagonal elements right here, this is x hat dot x hat, y hat dot y hat, z hat dot z hat. These are just the each of the covariant basis vectors dotted with themselves, and therefore these values are equal to the square of the magnitude of each of the vectors. So if we just take the square root of each of these guys down this diagonal, then what we're going to get is the length of our covariant basis vectors. So this result is related here by taking the square root of each of these guys, you'll get these. All right, next thing we want to do is to derive the, the metric equation, and the formula for that is ds squared equals Zij times dzi and dzj. Okay, in theory there are going to be 9 terms here. We iterate through I and j, we'll find an expansion of 9 individual terms. But we only need to consider the terms in which this factor of Zij here is non-zero. And here we only have 3 terms that are non-zero. So we can, out of the 9 terms that this might result in, we only need to see 3 of them. Okay, so here's what we do. We'll do ds squared equals z11 times dz1 dz1 plus z22 dz2 dz2 plus d, excuse me, back up, z33 dz3 and dz3. Okay, well now this guy is equal to 1 from over here. So is this one and this one. And we know that dz1 is really dx. So this is going to be dx squared. This is dy squared. And this is dz squared. Like that. Okay, so that means that our final answer is simply ds squared equals dx squared plus dy squared plus dz squared. And you'll see that right over here. Okay, finally, we'll look for the formula for the arc length, and that's easy because all we do is to take each of these guys, divide by a factor of dt down at the bottom here, place the whole thing under the radical, and in the integration sign, and we're done. It's a direct result of the metric equation to establish the formula for the arc length. Now I expect that you have seen these equations before. In your basic calculus you learned that this is the relationship of the arc length to the incremental displacements of each of the variables x, y, and z, and this I'm sure you saw as a formula for calculating the arc length. What's very fulfilling here is to see that the generic formulas we've derived for tensor calculus work in Cartesian coordinates. In fact, that's a requirement. We have to know that if we've got a formula that works for everything, well, it's got to work for the simple cases that we already know. All right, that's Cartesian coordinates. Let's quickly work through the others. Next, we'll consider affine coordinates. And in this case, we've already worked some previous examples, so we already know what the covariant basis vectors are. So what we're going to do here is to derive the covariant metric tensor. In this case, we're going to have a square matrix that has only 4 entries because we're working with a 2-dimensional space here. All right, the first entry, z11, is going to be this vector dotted with itself. So if we dot that with itself, then the result is simply going to be a squared. So we have a squared right here. All right, the entry 1, 2 is going to be the vector z1 dotted with z2, which means we multiply this term by this term and add the corresponding product of the y term here, but since there is none, this is really 0y, then this factor doesn't enter into it. So the result is simply the product of these two factors. So we wind up with a b cosine alpha, just like that. Okay, now because the tensor is symmetric, z12 is the same as z21, so we immediately know that this is ab cosine alpha. And finally, we're going to determine z2 dot z2. Well, that, in using the Cartesian form we have here, is just the square of this term plus the square of that term. So we'd have b squared cosine squared alpha plus b squared sine squared alpha. And I'm sure you can see that this is b squared times cosine squared alpha plus sine squared alpha, which in the end is just b squared because all of this is equal to 1. So this is just b squared right over here. Okay, so that represents our covariant metric tensor, and it looks just like this. All right, next, as before, if we look at the square root of the diagonal elements like this, we're going to get the magnitude of each of our basis vectors. And of course, this is consistent with what we already know. We analyzed earlier that the length of each of these basis vectors is going to be equal to the corresponding scaling factor, and indeed it is. Okay, now for the metric equation, remember it's ds squared equals zij dzi dzj. Okay, we'll just run through it quickly. ds squared is equal to z11, which is a squared, times dc1, which in this case is du, and dz1, which is also du. Now we'll add z12, which is ab cosine alpha, times dz1 dz2. Then the third term will be this factor over here, which is z21 ab cosine alpha times dz2 dz1. And finally, the zz2 term, which is b squared times dv dv. Okay, it's pretty easy to see that this will become du squared. And these two terms are the same. The only difference is the order here. So it's perfectly acceptable to write it down as 2 ab cosine alpha du dv. And the last term is just b squared dv squared. And that then is our metric equation for affine coordinates. And the arc length is very simple. Divide each of these guys by dt. Each one of these gets a dt denominator. Everything goes under the radical and in the integration sign. And that's the result for affine coordinates. A couple of things to point out here. Number one is that you'll notice everything in the metric tensor is a constant. There are no variables here. And that means that the metric tensor entries are going to be the same everywhere in the space. Now that is a unique feature for affine coordinates. It will not generally be the case for curvilinear coordinates. Second thing is you'll notice that the off-diagonal elements here are not zero the way they were for Cartesian coordinates. And the reason for that is that the two basis vectors are not orthogonal. If we do not have orthogonal covariant basis vectors, then we're going to get these off-diagonal elements. If everything is mutually orthogonal, then the only elements that will survive are the ones down the diagonal. Everything else will be zero. And finally, I want to point out that if you set A equal to 1, B equal to 1, and alpha equal to pi over 2, and substitute that into everything down the line here, what you're going to see is these results would exactly be the same as Cartesian coordinates because that's what they are when we set these values this way. Moving on to plane polar coordinates. Well, we know what the covariant basis vectors are there from previous work. So we're going to come up this time with a matrix of 4 entries because we're working in 2 dimensions. Alright, so what we need to do first is to find the value of z1 dotted with itself, which means squaring this term and adding the square of this term. Cosine squared theta plus sine squared theta, and of course you know that that's equal to 1. Alright, next we find the value of z1 dotted with z2, and that's going to be this term but multiplied by this term plus the product of these two terms. So it's negative r sine theta times the cosine of theta plus r cosine theta sine theta, and it's very obvious that these cancel out, leaving us with a 0 in this position. And of course, if z12 is 0, then z21 is 0 as well. And finally, z22 is going to be this term dotted with itself, which means we square each of these terms and add them together. R squared sine squared theta plus R squared cosine squared theta. Factor the R squared out. And we're left with just R squared. And that's this term right here. So we now have the covariant metric tensor that looks just like this. A couple of things to point out. Notice that we do not have any off-diagonal elements. The only ones we have are the diagonal, and that's a direct result of the fact that these two basis vectors are orthogonal. When that's the case, we only get the diagonal elements. Second thing is, notice that R is included in one of our elements here. It's not a constant value. So the value of Z22 is going to change depending on where we are in the space. As I pointed out before, that's going to be the case generally with curvilinear coordinates. Okay, next we can take this result and derive the magnitude of our basis vectors. These values are the square root of the column, or the diagonal element here, and that's consistent with what we know already. The R basis vector was a unit vector, and the theta basis vector was, you remember that it was tangent to the circle, and when that happens, the length of that vector is going to be equal to the radius of the circle. Okay, this time we can do the metric equation by inspection. ds squared is equal to z11, which is 1, times dz1, which is r squared, dr squared. And the only other term is this one, where we have z22, r squared, times dz2, and dz2 is d theta, so that's this. And that's the metric equation for plane polar coordinates. And then that translates immediately to the arc length. You know the drill here, divide everything by a factor of dt, put it under the radical and in the integration sign, and we're done with plane polar coordinates. For cylindrical polar coordinates, we know that our covariant basis vectors look like this. So we'll work through the example here. This time it's 3 dimensions, so our matrix will be 3 by 3. All right. The first entry is going to be dz1 dotted with itself, which means we square both of these. So cosine squared phi plus sine squared phi is equal to 1. All right. Second case is z1 dotted with z2, and that means we're going to have to multiply these two terms and add the product of these two terms. Well, you can see, I think, by inspection, negative rho sine phi cosine phi and positive rho sine phi cosine phi, that's going to be equal to 0. So z12 has to be equal to 0, and because of the symmetry, z21 has to be equal to 0. Okay, now we take z1 dotted with z3. Well, when we go to multiply this term by its corresponding x value here, there is none. There's no corresponding y value, and there's no z value here to correspond to this. So the dot product between z1 and z3 is equal to 0. That means that this is a 0, and because z13 is 0, then z31 is a 0. Okay, next we'll find the dot product of z2 with itself. That means we have to square this term and add the square of this term. Rho squared sine squared phi plus rho squared cosine squared phi, and surely you've seen this enough now to know that this is just rho squared. So z22 is rho squared, like that. And now, what's next? We have Z2 dotted with Z3. Well, the same idea before. There's no X or Y values here to correspond to these guys, so the dot product between Z2 and Z3 is going to be equal to 0. That means that Z23 is 0 and Z32 is 0. And finally, we need the dot product of Z3 with itself. That's easy. It's a unit vector dotted with itself, and that result is always 1. So this then is the covariant metric tensor for cylindrical polar coordinates. Now it shouldn't be any surprise to you that the results right here, these 4 entries, look a lot like plane polar coordinates if we had r instead of rho. And that's the case because cylindrical polar coordinates is really plane polar coordinates with this extra dimension down here. Okay, if we want the magnitude of our basis vectors, it's this. Take the square root of each diagonal term to get the magnitude of those vectors. And then we'll move on to get the, what are we looking for, the metric equation. So ds squared is going to be z11, which is 1, times dz1 dz1, which is going to be d rho squared. The second term is going to require z22 as a factor, and then dz2 times dz2, which in this case is d phi squared, plus 1 times the third dimension of dz3, which is dz squared. And that is our metric equation, followed by the formula for the arc length. Straightforward. Divide everything by dt, put it in the radical, and inside the integration symbol here. And finally, we'll look at spherical polar coordinates. Here are our basis vectors, and we have a 3-dimensional solution here, so it's going to be Zij with 9 entries. Okay, first thing we'll do is take the dot product of Z1 with itself. That means squaring each factor and adding it all together. So we have sine squared theta, cosine squared phi. Second term squared is sine squared theta, sine squared phi. And the last term is just cosine squared theta. Well, from previous work, I think you can see that those two terms together are just sine squared theta, because we could factor sine squared out, leaving cosine squared phi plus sine squared phi equals 1. And now this term added to that term is simply 1. Okay, now we take z1 dotted with z2. That means finding the product of these two terms plus the product of these terms plus the product of these. So that's going to be r sine theta cosine theta. In the first case, we'll have cosine squared phi. And here we'll have r sine theta cosine theta sine squared phi. And the last term is negative r sine theta cosine theta. Well, the same drill we've done before, because I have this, then this whole expression is just equal to the factor that we will take out of the expression. So r sine theta cosine theta is what these two terms resolve to, and of course that cancels out with this, meaning that the value of z12 is 0. And because of the symmetry, z21 is also 0. Next, we'll take the dot product of z1 with z3. That means this term times this one plus this term times this one. There's no z term here, so this doesn't have any effect. All right, we have r sine squared theta sine phi cosine phi, and it's negative because of this. And then over here we have positive r sine squared theta sine phi cosine phi, and the two cancel out. Therefore we find that z13 is equal to 0, and therefore z31 is equal to 0 as well. Next we need the dot product of z2 with itself. So that means we have to square this term plus the square of this term plus the square of that term. R squared cosine squared theta cosine squared phi. Second term squared is r squared cosine squared theta sine squared phi. And the last term is r squared sine squared theta. Okay, these two terms together, again, because we can factor out something and leave cosine squared plus sine squared behind, we'll get r squared cosine squared theta. And we combine this term with this one, we'll find it's just equal to r squared because we factor r squared out and this plus that is 1. Therefore, z22 is equal to r squared, just like that. Okay, now we'll take the dot product of z2 with z3. We multiply these two terms plus the product of these two terms. Negative r squared sine theta cosine theta sine phi cosine phi. This term is plus r squared sine theta cosine theta sine phi cosine phi, and the two cancel out, leaving us with a value of z23 being 0 and z32 is 0. And finally, z3 dotted with itself means that we're going to have to take the square of each of these two terms, add them together. R squared sine squared theta sine squared phi plus r squared sine squared theta cosine squared phi, and the same drill as before. When we see these things, we know that the end result is going to be just r squared sine squared theta. And that indeed is the value of z33. So there's our covariant metric tensor. And if we look at the lengths of our basis vectors, it's simply the square root of these items, giving us the magnitude of those vectors. Then if we want the metric equation, we only have three terms to consider. ds squared is equal to z11 times dr squared plus z22 times d theta squared, and z33 times d phi squared. So we can do that by inspection to get that result. And finally, the formula for the arc length. Now notice that our metric tensor elements are functions of r and theta. They're not constants. So this being curvilinear coordinates, that makes sense. Also notice that the only elements that survive are the diagonal elements, and that confirms what we already know, that each of these basis vectors are mutually orthogonal to each other. They're all at right angles to each other, so the only elements in the metric tensor that survive are the diagonal elements. Okay, the video is a little longer than normal, but hopefully it was beneficial to you in understanding the metric tensor and how to calculate it. Next time, we will introduce the idea of a contravariant basis.